Hi there, welcome to this next Integrated Math 2 video. Before we get into our lesson for today, go ahead and try these 3 warm-up problems. Alright, so in this case we've got number 1 here, convert this, this is factored form, converting that into vertex form. One of the ways we talked about in our last video is averaging the 2 zeros or the x-intercepts to get the x value of the vertex. Because if you think about it, if I draw a rough sketch here, we have our 2 x-intercepts, and a parabola is symmetric, right? So that means that the x value of the vertex should be halfway in between the 2 x-intercepts. And so therefore we can just average those 2 x-intercepts to find the midpoint between the 2 and go from there. So in this case, our zeros or x-intercepts are when x is -7 and when x is +5. So -7 and +5, and then of course there's the y-axis in there somewhere. But if we were to average these two, so add them together and divide by 2. So add these together and you get -2, divide by 2 and you get -1. So the x value of the vertex is -1. So we know that much. So -1, comma, something. And as always, to find the y value when we know x, we can just substitute it in, right? So let's go ahead and put -1 in for our function here. So see, -1 minus 5, I'll do this in green so you can see it. -1 minus 5 is -6. -1 plus 7 is +6. So we get -36 here divided by 2, because same thing as multiplying by half, right? So -36 divided by 2 is -18. And so -18, and my graph does not depict that because the actual graph is concave up. But either way, we were able to find out the x value and the y value of the vertex. Again, -1, comma, -18. And from there we can build the vertex form. So it's y equals a, which is 1/2, right? The a value is always the same no matter what form you're in. So a times x minus h squared. So remember, it's the opposite of this number here, because remember the x value of the vertex is whatever makes that 0. So to go backwards, we'll change the sign there to put it in. Minus 18. So that'll be the vertex form. And you can always check yourself. Graph both. Graph the standard form in your calculator, graph the vertex form in the calculator, and see if it creates the same graph. Just be careful because one of the graphs may be off the screen, so make sure and change your window around just to make sure that both graphs are actually identical. You can also go to the table of values to see that all the y values are identical for each x. Number 2, simplify this one here. We've talked about multiplying polynomials before, in this case 2 quadratics. We're going to start by multiplying the 3x squared inside the second parentheses, so everything in that second parentheses here. So we're going to have -12x to the 4th. All right, x squared times x squared, that means you have 4 x's being multiplied, so it'd be x to the 4th. And then -21x squared. Now we're going to multiply -x inside the parentheses. So it'll be +4x cubed and +7x. Now we're going to multiply the 1 inside, so it's going to be -4x squared minus 7. And then from there we can combine like terms and put it in standard form here. So we have -12x to the 4th. We only have 1 cubic term here, 4x cubed, so plus 4x cubed. We have 2 squared terms here and here, so it's going to be -25x squared. And then only 1 linear term, so it'll be plus 7x. And then 1 constant term of -7. So we multiply those together, we get that, what we call, it's a quartic is what it is, but that means, all that means is the highest power is 4. All right, number 3, let f of x equals absolute value of x. Compare f of x with g of x, which is negative absolute value of x plus 5 minus 3. So let's describe each one of these different changes here. So from here to here, If we go from this graph to this graph, it's going to be shifted left 5. So left 5. And then kind of work your way out from there. So left 5, as we talked about a long time ago, in a video a long time ago, why that is, but it's left 5. And then this negative out here is going to make it, instead of an opening up V, it's going to be an opening downward V. So opens down. And then lastly, this -3 here shifts it down 3 units. So left 5 units, opens downward instead of upward, and then also down 3 units as well. So just a recap, a review of something we've done in the past with these transformations. All right, up next, in this lesson, we're going to look at how to use what we already have learned to rewrite quadratics to tell us characteristics of that quadratic and its context. So for example, factoring, multiplying, completing a square, all of those skills that we've learned so far this unit, we're going to kind of put those together to rewrite quadratics in various forms to tell various characteristics of those quadratics. So to kind of recap all of those things, we've got this nice diagram here that we looked at in our last video. So we've got these 3 forms and various ways to get between those 3 forms. Keep in mind each form tells us something different. So factored form tells us the x-intercept really quickly. Standard form tells us the y-intercept. Vertex form tells us the vertex. And then all of them tell us the concavity and whether it's opening up or down. So just to kind of recap here, we've learned how to multiply polynomials. We've learned how to complete the square in our last video. We've learned how to factor in a previous video as well. And then, especially in our bell work here, we talked about how to average the roots to find the h value and thus get from factored form into vertex form. So if we think about those characteristics, x-intercepts, y-intercepts, vertex, what do those tell us about the context? Each one reveals something different about the context that we are talking about, whether it be a parabolic motion problem where we're thinking about something flying through the air, or we're talking about how profit changes over the course of months. Regardless, the vertex tells us the minimum or maximum value that the function takes on. It also tells us, if you think about the x value involved, it tells us when that occurs. So the y value is the max or min. The x value tells us when that occurs if it's in terms of time. So what month does that max or min profit occur? At what second does the ball reach the maximum height? That kind of thing. Concavity, and you can tell that from any form, tells us whether it is a max or a min. Right? If it's concave up, then you're going to have a minimum there at the bottom. If it's concave down, you're going to have a maximum at the top. And so it tells us whether it's a max that we're talking about or a min that we're talking about. X-intercepts, that tells us when the y value is 0. So when does the ball hit the ground? When does the profit break even? So when is the output, either height or profit or whatever it is we're talking about, when is that 0? So the x-intercept tells us that. The y-intercept, lastly, it tells us the initial height or the starting / current value of something. So what height are we throwing the ball from? At what's our current profit? Those kinds of things. So those are the characteristics and kind of how they connect with the context that we are describing. So in the next few slides, I've got a rocket task. So each one of these describes the flight of a rocket being launched. And each one gives us a different form of a function and asks us certain questions about that. So in number 1 here, for a science project, Larry designs and launches a model rocket from the rooftop of an empty building. He places a sensor on the rocket to provide him with data about the height from ground level in feet of the rocket over time, from the time of launch in seconds. From the data returned by the sensor, Larry was able to write a function modeling the height of the rocket over time. So this is a function that models the rocket's height over time. So H stands for height in terms of time. So we can put in various times for T, and it'll output the height of the rocket at that time. So that's the relationship there between height and time. So we've talked about the various characteristics of this quadratic and what that might mean. So it says find the y-intercept in part A here. It says find the y-intercept of this function, describe what the y-intercept means in the context of the situation. B says find the vertex and describe what it means in the context. And then C says find the zeros and what it means in the context. So you've got the tools necessary to do this. We've talked about how to complete the square, factor, multiply, those kinds of things. So you've got the tools to do this. So let me just give you some time to think through these three and see what you can do. Okay, so in part A here, the y-intercept, and we can actually see this right away in standard form. It's right here, right? It is the y value of the y-intercept. So our y-intercept is the point 0, 112. And that tells us in the context, let's see, didn't he launch it from the height of from the top of a building? So that means 112 feet is the height of the building that he's throwing it off of, or launching it from. So that's what the y-intercept tells us in the context. Part B, find the vertex of this function. Well, let's see. In our last video, we talked about completing the square to find the vertex. So let's do that. So we've got negative 16t squared plus 96t. Push the 112 off to the side. And let's go ahead and factor out the 16. So 96 divided by 16 is 6. So we can factor out the negative 16 here. That's going to give us t squared plus, or actually minus 6 t plus 112. And then we can complete the square, right? B divided by 2 squared. So negative 6 divided by 2 is negative 3 squared is 9. But remember, this is not just a 9. Everything inside the parentheses is being multiplied by negative 16. So by putting 9 here, we're actually adding negative 16 times 9 to the function. And negative 16 times 9 is negative 144. So we've really changed the function by negative 144. So we need to add 144 out on the outside here, leaving us with negative 16, this is again h of t, negative 16 times t minus 3 squared plus 256. So by converting it to vertex form there, we can now tell the vertex is 256. And the great thing about that is that tells us the maximum height and when that occurs. So the rocket reaches a maximum height of 256 feet 3 seconds into launch. And so by completing the square, we were able to reveal that characteristic of this rocket launch. Okay? All right, and then, so that was part B. Part C, I'll just go ahead and erase this. Part C says find the zeros and describe what those mean. All right, so in the zeros here, to find the zeros, we need to get to factored form. One of the first things we always want to do when getting to factored form is look for a GCF to make the factoring a little bit easier. So let's see if we can actually factor out a negative 16 here. So let's see, 96 divided by 16 we said was 6. 112 divided by 16 is 7. So let's go ahead and factor out a negative 16 from the function. So t squared minus 6t minus 7 is h of t. So now we can factor the inside piece here. So what multiplies to give us negative 7 that adds to give us negative 6? Hopefully you're thinking -7 and +1. So we have h of t is equal to this in factored form. So we've converted it to factored form, which allows us to tell the x-intercepts. So what value makes this 0 and what value makes this 0 using that zero product property. So t equals 7 and t equals -1 makes that happen. So again, just to recap, we factored out a -16 to begin with, which allowed the factoring to go a lot simpler here, a lot quicker. If you wanted to use factoring by grouping, you could definitely do that. It just might take a little bit more time. Always look for a GCF though, if you can, when factoring. So what does this tell us? Well, let's see. If we were to maybe create a quick sketch of this graph here, up and back down. Again, not a perfect graph. We know the vertex here is after 3 seconds. It's at 256 feet. Here's 112 where it starts. Here's at -1 seconds, and at 7 seconds, we have those x-intercepts here. So after 7 seconds, the rocket hits the ground. So that's the time of its flight. So it's a 7-second flight. The -1 second, it actually doesn't mean anything in this context because the rocket launches at 0 seconds, right? T minus 3, 2, 1, liftoff, right? Liftoff happens at 0 seconds. So the -1 in this case does not mean anything in terms of the context. All right. So we've got our information for this rocket launch. Everything we can know about this rocket so far. All right. Let's go on to our next situation. This time we have John, and John designed a rocket and gathered data for its flight. John was able to use the data to write a function modeled by the height y from the ground level of the rocket over time. So similar situation, right? Y is height, and then in terms of t, it says find the y-intercept, vertex, and zeros, and see what those mean in the context. So again, let me give you some time to think this through, see if you can come up with those 3 items and then what those mean in the context. All right, so in this case, if we go back to our last example, it was the y-intercept that was easy to see. In this case, the y-intercept is not so easy, but what is the zeros. So I'm going to circle C because the zeros are really easy to see given factored form. In fact, we can go ahead and do this. Let's see, t equals 18 and t equals -2. Again, going back to our last example, the -2 doesn't mean anything. It's only the 18. So we've got an 18-second flight here for this rocket. All right, the other 2 are not as easy. Let's see, the y-intercept is always the y value when x is 0, or in this case, when t is 0. So if t is 0, we're going to have -16, 0 minus 18, 0 plus 2. So it's going to be -16 times -18 times 2. So let's see, 16 times 18 times 2 is 576. So 576. So our y-intercept is 0, 576. And again, all we did was we put 0 in for our x value, or t value, and then see what the y value is corresponding to that. So again, that means that it was launched from a height of 576 feet. Now we don't know what it was launched from, maybe a higher building, something like that, who knows? All right, find the vertex. So again, going back to our bell work, we can average the 2 zeros here. So our zeros, our x-intercepts are 18 and -2. Add those together, you get 16. Divide by 2 and you get 8. So that means the x value of the vertex is 8. Okay? We don't even actually have to find vertex form here. We could just substitute 8 into our function and see what we get out, and that will give us the vertex. Okay, and again, we got the 8 by averaging the 2 x-intercepts here. All right, let's put in 8. So -16 times 8 minus 18 times 8 plus 2. So we get -16 times 8 minus 18. Let's see, it's -10. times 8 plus 2 is positive 10. Okay, so we can use some mental math here. See, 10 and negative 10 make negative 100. Negative 100 times negative 16 is positive 1600. So 1600. So that one actually got really, really high. So after 8 seconds, it reached a maximum height of 1600 feet. So much higher than the previous rocket. All right. And again, you could have multiplied this out to get to standard form, and then completed the square to get to vertex form, and then you could find the vertex from there. But one way to get from factored to vertex is just to average the zeros or x-intercepts. Okay? And our last example here, I'm going to move this over a little bit so you can see it. We have Sherry, and she collected the following data from a sensor and a rocket she designed and launched. Examine the data and find the following. So we got our table here. X is in seconds across the top, so 0 seconds, 1, 2, 3, 4, all the way to 7. And then Y is in feet here, and it starts at negative 160 and goes up from there and then down there at the end. So again, we're looking for the y-intercept, vertex, and the zeros or x-intercepts of this rocket launch. So take some time and see if you can figure out those three and what they mean in the context. All right, so in A, the y-intercept. So the y-intercept is the y value when x is 0. So there's our y-intercept right there. So 0, comma, negative 160. So that means that the rocket was launched 160 feet below ground level. So maybe it was launched from a bunker or something. All right. So that's our y-intercept and what it means in the context. B, find the vertex. So if we look at this, it goes up, 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 then back down. I hope that you see the symmetry right here. Whoops. Right here at 6. All right, it goes up, and then it reaches its maximum, and then notice 120 and 120. Right? Remember, a quadratic is symmetric across the axis of symmetry or the vertex, and so 120 on either side indicates that 6, 128, this one right here, is our vertex. So we can see that there. So that's going to be 6, 128, which means after 6 seconds, our rocket reached its maximum height of 128 feet. All right, and then lastly, find the zeros of this function. Okay, so the zeros are x-intercepts. That's when the y value is 0, right? The height is 0. So I'll do this in blue here. 0 is right here, right? The height is 0. So that's at x equals 2 or 2 seconds. All right, let's find the other one. So we have to use the fact that a quadratic is symmetric to figure this one out. So if we were to continue the table, continue this out, okay, after 8 seconds, well, let's see, 128, 120, 8 would be with the 4 here, so 96. 9 would be with the 3, so 56. 10 would be with the 2, so 0. So by extending the table out there to find the other point when y is 0, allows us to find the other x-intercept. So it's at 2 seconds and at 10 seconds. Okay, and in this case, both of these numbers actually mean something in our context. So if we said earlier that it was launched from a bunker, right? So if it's launched in the bunker and it goes up, at 2 seconds is when it crosses through the ground level. So when it comes out of the ground after 2 seconds, and then it goes up in the air, and then it comes back down after 10 seconds. So these actually both mean something in the context of this situation. So I hope that kind of gives you an idea of not only how to convert from different forms, but also what is best for various characteristics. Like for vertex form is best to find the vertex and thus the maximum or min. Factored form is best for x-intercepts. Standard form is best for y-intercept. So there are various advantages to each of these forms. All right, in our last example, I want to give you some time to try it and see what you can do, and then we'll talk about it here in just a moment. All right, so we've got a 500-foot roll of fencing and a large field. You want to construct a rectangular playground area. What are the dimensions of the largest such field or yard? What is the largest area? So we can start by thinking about area. So we have area and perimeter. So perimeter equals 2L plus 2W, right? And then we also know that area is length times width. And if we were to draw this, so we have W here, L here, and of course the area is going to be L times W. All right, so the sum of all of the length around here, which is the perimeter, should be 500. So we know that 500 equals 2L plus 2W. All right, well, from there we can actually, if you notice, everything's divisible by 2 here. So let's go ahead and divide everything by 2. So it would be 250 equals L plus W, which means that we can solve for one of these. How about W equals 250 minus L? So what we're doing here is we're relating the perimeter to the area by using this process here of solving for one of the variables. So if we can solve for L or W, we can actually substitute this back into here. So area is equal to length times width, which is 250, minus the length. So I hope you're seeing a connection there, right? W, this is W. And now we want to convert this to vertex form so we can find the maximum. All right, so if you weren't able to get started, go ahead and take some time and see if you can finish this off to find the vertex form of this quadratic. Just use, L as your X and of course A as your Y. All right, so let's go ahead and distribute the L. So we have L times 250 minus L squared. And if it makes you feel better, we can go ahead and put the L in front. And if it makes you feel even better than that, we can use X instead of L. So plus 250, 250X. All right, so from there we can complete the square. So let's factor out a negative from the first two terms here. So we negative 250X. And then from there we can complete the square. So 250 divided by 2 is 125. And of course 125 squared is 15,625. So 15,625. But really, it's not just 15,625. It's 15,625 times a negative 1. So really, we're subtracting this amount from our function. So as a result, on the outside, we're going to add 15,625. All right, from there, we can factor. So it's going to be minus, X minus 125 squared plus 15,625. Which gives us a vertex of positive 125, comma, 15,625. So what that tells us is when what do we solve for here? we were dealing with x, but really it was L that we were working with, right? So when the length is 125, and in fact it would be the same for the width as well, but when the length is 125, we get a maximum area of 15,625. All right, so if we go back up here, if we put 125 in here, like I said earlier, if you put 125 in for L, 250 minus 125 gives you a width of 125. So what we're saying here is the area is maximized when we have a square. So really, you could have taken a little bit of different approach to this problem if you'd known that ahead of time. But by doing this process, we have discovered that the maximum area is gained by making it a square. And we may have talked about this earlier with difference of two squares and seeing that, but this confirms that. And so by completing the square and converting it from what was originally factored form to standard form to vertex form, we're able to find not only the maximum area, but what width or length creates that maximum area. Okay? So I know that was a little more challenging problem, but hopefully through the course of today, you've been able to see how to not only write quadratics in various forms, but how that helps us gain or understand the characteristics of the quadratic a bit more, and the reasons for having those various forms. Obviously, technology can help us do this as well. If you're given it, you can always graph it in Desmos or on your calculator and find the characteristics that way as well. But again, you're still going to have to understand those characteristics in the context of the problem and what it means and that sort of thing. All right, so hopefully you'll join us in our next unit, which gets into solving quadratic equations. And as I said earlier in our last video, we'll even learn a formula for the h value of the vertex. So hopefully you'll be able to join us then.